All right. So we're going to be looking at some 3D surfaces now, and these are all going to be surfaces where the equation that defines them has, typically they're going to have squares in them. So for the cylinders and quadratic surfaces, when I say squares, I mean like variables squared. You'll see what I mean. So first off, we have cylinders. So a cylinder is defined as a surface that consists of all the lines, also known as rulings, that are parallel to a given line that pass through a given plane curve. For example, if the plane curve that you're looking at is a circle, and I'm drawing it here in 3 dimensions, kind of with a little bit of perspective, and if you draw a line that goes through this, all the other lines that go through it are going to be, like this one, say, intersects there. You can see what you get is an infinitely long tube, right? That's a cylinder. I'm not drawing all of them, but like there's an infinite number of lines that are going to be parallel that are going to intersect this curve, or going to make kind of extrude the curve. So if you, it doesn't have to be a closed curve. It could be something like this, and the cylinder might look something like this. So a cylinder in this, whatever this planar curve, whatever that is, so you have this kind of like a big ribbon of fabric, kind of just kind of waving through the air. The lines that define this, that are all parallel to each other, they don't have to be perpendicular to the plane. They can be like at a slant or something. That's fine. That's how you define a cylinder. For example, if we looked at z equals x squared, it would look like this. So you have, if you look in the x direction and the z direction, what you're going to get is a whole bunch of these parabolas. And each of, like this, for example, is the z equals x squared with y equal to 0, but maybe over here you've got z equals x squared and y equals 1, and so forth. So for all the different values of y, you would have a different parabola, and then all of those kind of stacked together gives you this long parabolic cylinder. Another example would be x squared plus y squared equals 1, and this would look like this. And so for any value of z that you pick, so let's say if we took z equals to equals 1, it's kind of might be hard to see exactly where this is in 3 dimensions, but this is approximately, it should be crossing over at 1, making a circle on the xy plane, right? That's x squared plus y squared equals 1 with z equal to 0. But if you set z equal to, say, 4, then you're going to get another circle, right, over here. And so for all values of z that you could pick, you're going to get another circle. All those stacked together give you this this circular pyramid, or circular cylinder. Here's another example. Now, because for this one's y squared plus z squared equals 1, you can see in the x direction, for any value of x you pick, you're going to get a different circle, right? So this is my attempt at illustrating this, going through the proper points. So here's the circle. This is where x equals 0, and then when you have here, this is going to be approximately when x equals -1. Here's the circle that you get when you let x equal +1. Of course, it continues around the other side, right? Each of these, setting the free variable, when you set x equal to some constant, you get a circle in space. And this is called a trace. And by thinking about where these traces are and what they look like, you can get a sense of what this looks like in 3D space when you have a cylinder. So a quadratic surface is a second degree equation in 3 variables. So the cylinder just had 2 variables in it. If there's 3 variables involved, it will be a quadratic surface. We're going to categorize those, but the most general form of a quadratic surface is this. So ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. Now, this is bigger than we're going to ever use. If you have it, all of these combined terms, the dxy, the exz, and the fyz, those terms really are going to have an effect of a rotation, what's called an affine rotation. It's like rotating it in 3D space. However, if we're able to just translate this thing by rotating it, we can actually translate all quadratic surfaces into one of 2 forms. So either ax squared plus by squared plus cz squared plus j equals 0, or ax squared plus by squared plus iz equals 0. And now a through j are all real numbers, either positive or negative. And so what we're going to see is by whether they're positive or negative and all of those combinations, we're going to get a bunch of different shapes. In order to get a trace, what we can do is, to get a trace, you can just set x, y, or z equal to some constant, and then you can see what, in a plane, what kind of shape you're going to get. Let's look at some examples. All right, so say we have the quadratic surface x squared plus y squared over 9 plus z squared over 4 equals 1. This is what it would look like graphed out. And you can, if we were to, for example, set each of these variables equal to 0 one by one, let's say we set, if x equals 0, you're going to get y squared over 9 plus z squared over 4 equals 1. And what you'll see, what that comes out to be, if you recall, is you get an ellipse with y, the y-axis having a what's the proper term? It goes 3 out in either direction. So this would be the trace where x equals 0. Here's the trace where x equals 0. If we let y equal 0, we're going to get x squared plus z squared over 4 equals 1, which is an ellipse with an x, so to speak, radius of 1, and a z, so to speak, radius of 2. And so the trace is going to look like this, where you've got a little ellipse going in on the xz plane. And lastly, if you let z equal 0, you're going to get x squared plus y squared over 9 equals 1. And this is going to look like this. So you have this ellipse going on the xy plane. So when z equals 0, you get x squared plus y squared over 9 equals 1. So the point here is, by looking at just the traces and just knowing that all 3 of these traces are ellipses, this thing is what's called an ellipsoid. So an ellipsoid, all the traces are ellipses. An elliptic paraboloid has ellipse traces parallel to only one plane, and it's got parabola traces in the other 2 directions. Here's an example: z equals 4x squared plus y squared. And here's what a graph of this would look like. You can see that if you set z equal to any constant, what you're going to get is an ellipse, right? But if you set x or y equal to a constant, what you're going to get is z equals either 4x squared plus a constant, or z equals a constant plus y squared, which is going to look like, here's what the traces look like in those directions. So here's a few traces where y is set to a constant. And when you set x equal to a constant, you're going to get traces that are going to look kind of like this. right? So altogether you can see how the traces in those two directions are parabolas, but in the other direction it's a bunch of ellipses, an elliptic paraboloid. The hyperbolic paraboloid is kind of like the cousin of the elliptical paraboloid, whereas in the elliptical paraboloid all the parabolas were opening in the same direction. A hyperbolic paraboloid is going to have parabolic traces that are opening in two different directions, which is say one, for example, opening upwards, the other one opening downwards, but on two different planes. And then you'll have hyperbolas in the third planar traces. Here's an example: z equals y squared minus x squared. So you notice how the signs of the x and the y coefficients are opposite each other. So here's what the surface would look like. And to illustrate the traces, let's just look. If we set say y equal to 0, what we're going to get is this. So y equals 0 and z equals negative x squared. And the other traces are all going to be parabolas. You can see where y is set to some constant, you're going to get a parabola that's opening downwards on the parallel to the zx plane. However, if you set y equal to a constant, if you set x equal to some constant, let's take x equals 0. So if x equals 0, you get z equals y squared, and this is a parabola that opens upwards. This parabola is now on the yz plane. But all of these parabolas that when you set x equal to any constant are going to be parallel to this plane and also opening upwards, as you can kind of see here. Now, it may not be quite so obvious from this picture what happens when you set x or z equal to some constant, but we'll see now by setting z equal to a constant. When we set z equal to, say, this is maybe approximately at 10, if z equals 10, you're going to get a hyperbola on this plane that's opening out to the y direction. But if z was some negative number, say negative 10, you're going to get hyperbolas that are opening out along the x-axis. You can see that. Now, I know it's getting a little messy with all of these lines, but hopefully you can picture. Now, a hyperbolic paraboloid, I just like to think of them as Pringles. They're basically a Pringle shape. And if you can picture a Pringle shape in your head, then hyperbolic paraboloids are no problem. So last we have hyperboloid. A hyperboloid of one sheet is going to have hyperbolas in two directions, and then there'll be ellipses in the third direction. So here's an example. We have x squared over 4 plus y squared minus z squared over 4 equals 1. And this is what a hyperboloid of one sheet is going to look like. So if you set y equal to some constant, what you're going to get is a bunch of hyperbolas, something like this. And then if you set x equal to some constant, say 0, you're going to get hyperbolas that are going to look like this, right? So you can see you got hyperbolas in these two directions, but you've got ellipses in the third, right? You can see all of these ellipses. You have ellipses for any constant z that you fix. You can see that the equation, so let's say if you set z equal to 0, you're going to get x squared over 4 plus y squared equals 1, which is the equation of an ellipse. And for any constant you pick for z, you're just going to have a different sized ellipse, right? So that's an elliptic, this is a hyperboloid of one sheet. So it's as distinct from a hyperboloid of two sheets, which you actually get if you have a different constant on the other side, you might have this not connected. These are actually a special case of this is what's called a cone. If the constant on the right-hand side actually is 0, what you're going to get is a cone. I'll show you what that looks like. So when you have a cone, if you set you've set x or y equal to 0, you're just going to get these straight intersecting lines like an X. But you still get hyperbolas showing up for these traces, right? You've got hyperbolic traces and you've got elliptical traces. Okay, so this is what a cone would look like. Now cones, in the geometric sense, they're actually, what we think of as cones is just 1/2 of this. But in fact, a cone opens up in the two directions. Anyway, we don't have to classify the cones too much. Just wanted to show you an example. So here's an example where we want to reduce it to a standard form to kind of figure out what quadratic surface this is. So what we'll want to do is to complete the squares and then figure out what we got. So we have the 4x squared. There's no other x terms, so that's fine. Then we've got y squared. We've got y squared, and we have minus 4y. And we've got a 4z squared, and we have minus 24z. I'm going to leave a little blank spot because I know I'm going to want to complete the square. And I'm going to actually put the equal 0. So I know what I need to complete the square for each of these terms. For the y, I need to take half of that minus 4 and then square it and add that. So it's actually going to be a plus 4, right? Adding 4 is only okay as long as I subtract 4. So I'm going to subtract 4 outside there. So y squared, I take it's minus 4 divided by 2, and then I square it in order to get, I actually want to be a little bit more careful with my z's. Before I complete this square, I want to factor the 4 out from both of these terms. So actually I'm going to write plus 4 times z squared minus 6z, and then I'm going to use this to help me do this. Completing the square here, take half of that 6. If that's a 3, that's going to be plus 9. So what I've done here, I've added 4 times 9, added 36, so I have to subtract 36 to compensate. Okay, so we have plus 36 minus 4. What I'm going to write this as now, 4x squared plus y minus 2 squared plus, that's 4 times z minus 3 squared minus 4, right, equals 0. And now it's worth observing, excuse me, I could translate this if I moved plus 2 in the y direction and plus 3 in the z direction. This would give me 4x squared plus y squared plus 4z squared. I could write equals 4. And I can divide everything by 4. I get x squared plus y squared over 4 plus z squared equals 1. This is an ellipsoid. That's an ellipsoid. And we can also just, we can check this. Well, actually, let's try just sketching it, and we'll see how well we do with that. So if we were to set, say, y equal to 0, what we're going to get is a circle, right, with a radius of 1. This is a little bit off. Let's 1 here, -1 down here. 1 and -1 out in that axis. So this is my approximate trace when I set y equal to 0. If I set z equal to 0, x squared plus y squared over 4 equals 1 means that y will have a y radius of 4. That's at 4. We have -4 out over there, and so when z equals 0, it's going to look something like that. And if we set x equal to 0, well, we already have these intercepts, so it's just going to complete this. We're going to have an ellipse. So here's my sketch, and we'll see what this thing actually looks like. And yeah, that looks pretty good. You know, I already told you I was shifting this thing over. What was I doing? I was 3 units in the, I was doing what, 2 units in the y direction and 3 in the z direction. something like that. But like I said, you can use translation to like put this into one of the standard forms, but you can see it's still this like oblong ellipsoid. So that's good. Here's another example. Let's try to figure this one out. And I'm going to go through the same process of completing the squares in order to get this into one of the standard forms. So I'm going to start with the x. We have x squared minus 4x. I'm going to leave this blank. We've got minus, we have y squared, and I'm going to actually be careful with, I'm going to put the y's inside the parentheses in order, and so that's actually going to be a plus 2y. And then I'm going to have plus z squared, and I have minus 2z, and I'm going to leave this blank, and I have the plus 4 equals 0. So we're going to adjust this stuff. I'm going to move this over. All right, so we'll complete each of these squares one by one. To complete the square for the x's, we need to add a 4, right? That's going to be half of minus 4 squared. And for the y's, I'm going, but actually, I don't want to forget, I have to subtract 4 outside the parentheses because that keeps things in balance. For the y, I'm going to be adding a 1, but keep in mind, there's a minus in front of that parenthesis. So actually, from the whole thing, I've subtracted 1. It just looks like a plus 1 because it's inside the parentheses. So because I've just subtracted 1, I need to add 1 in order to make things whole again. And for z, I'm going to also add 1, which means I'm going to subtract 1. Okay, so what is this going to look like? We've got x minus 2 squared minus y plus 1 squared plus z minus 1 squared equals 0. By translation, you can translate this by shifting it over 2 in the x direction, negative 1 in the y direction, and 1 in the z direction. We're going to get x squared minus y squared plus z squared equals 0. And what does that look like? Let's try to sketch. Well, first let's classify this. This is a hyperboloid of one sheet. And I know that because when you have all 3 terms squared, but the one of them has the opposite sign of the others, that'll be hyperboloid of one sheet. In fact, this is the cone example that we were just looking at. Let's sketch this out and see how it looks. Let's attempt to sketch this out. I'm going to start by figuring out what this looks like on the xy plane. So when we set z equal to 0, we're going to get x squared, minus y squared equals 0. And that graph is going to be all of the lines where x equals plus or minus y. So we're going to have this x, 45 degrees from the x and the y axes. If we set x equal to 0, so this is going to be on the yz plane, you're going to get z squared equals y squared. Well, you could write it like that, z minus y squared equals 0. This is going to be on the xy plane, so I'm going to draw it like this, and I know this is going to be really hard to look at. But now we can actually start to see what happens when we set if we set y equal to some constant. We're going to get x squared minus constant squared plus z squared equals 0, which is actually x squared plus z squared equals a constant squared. So what we get finally to like tie this thing together is a bunch of these circles opening up in the y direction. And finally, we can kind of picture this thing. So we have a bunch of these cones opening in these 2 directions. This is what we would expect it to look like. And let's take a look at the graph. And this is good. This is pretty much what I expected. I mean, I think you know that I translated the whole surface over by a few units, but it still looks pretty much the same. That's good. So now we'll generate a quadratic surface geometrically. We're going to find the equation of all the points that are equidistant from this 1 point, 0, 1, 0, and the plane y equals -1. And so for some x, y, z, the distance from the point, distance 1 would be the square root of x minus 0 squared plus y minus 1 squared plus z minus 0 squared. That would be the distance 1. The distance from this point to that, from the xyz to 0, 1, 0 would be my distance 1. Then distance 2 is going to be the distance between this and the plane. Now, the distance between a point and the plane y equals -1, it doesn't matter what x and z are. It just matters what is the y coordinate. It's going to be simply the square root of y minus -1 squared. That will be the distance. So it doesn't matter what x and z are, because we just want to know how far is the y coordinate away from -1. Let's clean these up a little bit. So we have these two square roots. And okay, so now how do we get the surface from these two? Well, we want the distance to be equidistant. So if we set the two distances equal to each other, it'll define a surface. Let's just define it, set square root of x squared plus y minus 1 squared plus z squared equal to the square root of y plus 1 squared. In fact, those things under the square roots are positive. You can square both sides and we'll be fine. So we can actually just write x squared plus, I'm going to actually expand this out because you'll see why, x squared minus 2y plus 1 plus z squared equals, on the right hand side, expanded out, foiled out, I mean, 2y plus 1. And now I can actually collect terms onto the left. And when I do that, I'm going to get x squared. The y's are going to cancel, but I'm going to have minus 4y, right? I'm going to have the ones are going to cancel, but I'm going to have a plus z squared equals 0. This is the equation. And if you're interested what this looks like, let's just plug it in and see. Let's graph it. So here's the graph, and you can see that it may be not so obvious that that's the point of intersection of this plane y equals -1, and so there's actually this distance of 1 unit away from this, what is actually the vertex of the paraboloid, and then you have this as also a distance of 1. Here's the point. So all of the points here, if you draw the distance to that point, that's actually not, so let's take this point here. If we were to draw the two distances, go from that point on the paraboloid to this point 0, 1, 0, and also if we were going to go to the plane, it's going to be the same distance. Of course, it's hard to see that when it's in perspective, but that's the way this thing is defined. All of the points on here are such that if you were to draw the orthogonal distance to that plane, it's the same as the distance to that point. These are orthogonal right angles I'm drawing here. So these are two congruent lines. But okay, so you can see that similarly, if you remember from these from the 2D analogs like the parabola and stuff, that's the way a parabola is defined. You have a directrix and a focus. Is that the right word, directrix? I think so. Anyway, a parabola is defined in that way. So a paraboloid, it should come as no surprise, is defined in a similar way in 3D space. All right, that does it for quadratic surfaces and cylinders. And we'll do some more practice trying to, really the big thing here is we're going to be doing a lot of calculus on these 3D surfaces or related to these 3D surfaces. So it's important to have a somewhat intuitive grasp of what they are. When you see the equation, you want to be able to think about what it might look like in 3D space, and it just comes with practice. All right, that's it. Bye.